This presentation is part of the PhD forum at ISE 2020 and is meant to be a companion of the poster that has been uploaded on the ISE 2020 website. In the exascale era, one of the most important things that we need to overcome is the challenge of bulk synchronous computing. Within bulk synchronous computing, multiple parallel tasks synchronize between the different iterations or steps, and this synchronization can completely kill the performance when there is a load imbalance in the system. Our objective is to remove this synchronization and allow scalability among thousands of cores. Our end objective is also to develop scalable solvers for the multi-GPU clusters, and we want to show that the asynchronous iterative methods can be the answer. We study Schwarz methods. Schwarz methods are a type of domain decomposition methods which were first developed by Schwarz to show the convergence of the Laplace problem in a domain decomposition setting. So the problem, you can see the schematic here where you have a global domain of 36 grid points where each grid point stands for an unknown. You decompose each of the larger global domain into smaller subdomains, 9 here, and each subdomain contains 4 unknowns locally. The green points form the interior of the domain, and the blue points form an overlap. Now, for an overlapping Schwarz method, the grid points that are the conjugation of the green and the blue ones are local to the subdomain, and the red points form the hero cells from which data needs to be exchanged with the neighbors. Now let us look at the core algorithm of our implementation. There are two main steps. First is the initialization, and the second is the solve. In the initialization step, you do first a partition of the matrix, distribute the data, and form the local subdomain matrices and the local right-hand sides in the distinct subdomains, and then you initialize some of the other buffers and data that you need. In the solve step, first you locally solve the matrix, you exchange the data, you update your boundaries, and then you check for convergence using convergence criteria that we will not go into too much in this talk here. All of our code is open source, and you can have a look at the implementation at the link given here. We use the Ginkgo library to handle all our arrays and to perform the local solves. And we use the CUDA-aware MPI within the Spectrum MPI of IBM to communicate between different subdomains. The results, the left plot shows the time per iteration of the synchronous case versus the asynchronous case. In the synchronous case, because of the global synchronizations, a lot of time is wasted in the boundary exchange. Even though we use the overlapping of the communication versus the computation, this cannot be hidden so much. The asynchronous case, as this has been completely decoupled, the computation and the communication, we see that per iteration, you save a lot more time. The right bar plot compares the different types of partitioning schemes for the synchronous version. Here you see that the Mattis partition is much more efficient in distributing the data to the different subdomains, whereas the regular 1D partition cannot do so well. Finally, we show some speedups of the asynchronous version over the synchronous version. On the left, we see the relative speedup of the asynchronous version over the synchronous version for 3 different partitioning schemes: the Mattis, the regular 2D, and the regular 1D, from about 4 subdomains to 100 subdomains. The top right plot analyzes the subdomain update spread between the synchronous case and the asynchronous case. In the synchronous case, all the subdomains perform the same number of subdomain updates. This is not the case in the asynchronous solve updates, but the overall medium number of updates in the asynchronous case is lesser than the synchronous case, and the median update multiplied by the lower time per iteration of the asynchronous makes the asynchronous overall faster than the synchronous case. And finally, to conclude, we saw that the asynchronous methods can provide significant benefits even in the case of GPUs and multi-GPU clusters. We saw that the benefits can increase as you increase the number of subdomains. For more information and detailed analysis, you can refer to our paper, which is on arXiv, as you can see the link here. Thank you.